Okay, so here on the second presentation for Chapter 25, I want to continue talking about a few topics from the first presentation. Specifically, what I'm thinking of here is this topic of constitutional isomers and then the substituent groups. I'm going to extend this to other functional groups, and I'm going to talk about additional substituent groups that we need to know. Like methyl and ethyl were the two that we saw in the first presentation. We'll see 3, 4 more for this one. I am going to stick with the what's in Brown and LeMay. I'm not going to add any more to the list. It's actually in your textbook. And what's new for this particular presentation is another type of isomerism known as stereoisomerism, and that one is specifically coming into this alkene discussion that you'll see in a few minutes. In this group of nomenclature, we're also going to do two others, cyclic alkanes and cyclic alkanes and alkynes. And the rules that we laid down the first presentation are going to be used with slight modification as we go through the rest of the nomenclature. So that, in some ways, that statement applies to all functional groups, even the ones we don't study. If you take organic chemistry, you'll see that systematic approach repeating itself over and over again. But the first thing I want to do is get back into this notion of isomerism, and then specifically for a series of alkanes. I have pentane here, which is a 5-carbon chain. And let me share something with you here for your alkanes. Alkanes, they actually follow a particular ratio between the carbons and hydrogens. Whenever you have an alkane, whether it's a straight chain alkane that we have here, or these are branched, the two other constitutional isomers for pentane, they all follow, well, one thing, this series, they all have the same molecular formula, which is one criteria for being a constitutional isomer. And then, like you see, they have different connectivity. But just a little comment about the molecular formulas for the alkanes. I'm going to give you a ratio here that is useful. If you need to be able to identify whether a molecular formula is an alkane or not, an alkane always follows this particular ratio of carbons to hydrogen. So to connect this formula to this molecular formula, the N in this example, well, it just simply represents the number of carbon atoms in your molecule. And so in this case, it's N. If you plug in, if N is equal to 5 in this case, if you plug in 5 into this formula here, 2 times 5 is 10, plus 2 is 12. This ratio indicates you have a saturated hydrocarbon. If you look at your big list of hydrocarbons, that rule is followed for all of these. And so it can be a useful way of recognizing whether you have an alkane or not. For example, if we were dealing with, well, a 20-carbon alkane, which we won't name, but you should be able to recognize whether you have an alkane or not based on that formula. Well, in this case, N is equal to 20. Remember, the ratio for the hydrogen is 2N plus 2, given on that first, the previous slide. And so, 2 times 20 is 40, plus 2 is 42. And so what it does, it establishes the molecular formula for this particular saturated hydrocarbon. Okay, so again, this can be a useful one to remember, and I'll show you two others as we go through to be able to recognize alkenes or alkynes, meaning do we have a double bond or a triple bond in our molecular formula. And just as a side note, if you take organic chemistry, these formulas are used can be used even more than what I'm describing. So I'm just really touching on 3 bases, and it's just a small portion of how these formulas can be used. But let me look at the constitutional isomers here, because that adjective, constitutional, is telling you a very specific type of isomer in front of you. Again, same molecular formula, which is true for all isomers, and then what's after that dictates what kind of isomer we have. In this case, since these 5 carbons and 12 hydrogens are connected differently in each of these molecules, these different connectivity, then we have constitutional isomers here. And what happens is you go from the straight chain and you slowly start bunching up the molecule. It starts becoming more like a sphere. And that does have consequences for its chemical and physical properties. Remember, one thing I talked about in the first presentation is a structure-function relationship. So it is a big deal. Here we can't get into too much of a discussion about it, because it takes a few months to sort of develop this notion and how it's related to the different aspects of organic chemistry. But we can get a little bit of a glimpse here. So structure. What I'm talking about is what do the molecules look like physically? If we were able to take a snapshot of these things. So the structures here are changing the function for each of these isomers. Now the function in this particular context are really the physical properties, which are listed down here with the names of the molecule. What you can see, and let's just look at boiling point. What we see is that the boiling point decreases as we go into a more highly branched molecule, which is, well, what you need to know. So boiling point decreases as you get more branching in a set of constitutional isomers. What's happening is that this straight chain, remember, it's really, well, you can see it here. You have this carbon backbone that's a zigzag. This zigzag allows for these molecules to cling to each other a little bit more effectively. What's happening for this example is the intermolecular forces. Are increasing for this one. When these molecules come together, they just stick together more effectively because there's more surface area for them to cling to. Whereas in this sort of, you can almost see it's spherical in shape. These spheres are just less sticky, if you will. They have a lower set of intermolecular forces, and as a result, you can see there's a lower boiling point that is needed to get the transition from a liquid to a gas here. And that's really about as far into structure function that we can really get into with the time that we have for this topic. The other thing that you should note here are the names for the isomers, and I'm not worried about isopentane, neopentane. If you take my organic class, you can learn those. I want to stick with the systematic names that you see here, what's called the IUPAC names. And they're laid out just like I did before, and I'm going to sort of quickly go, since we've already done Alkane nomenclature, I just want to point out what's happening here. So, if we have a unique compound with unique chemical and physical properties, then we need a unique name for each of those compounds, even if they have the same molecular formula here. And so, pentane is just taken from the table for the straight chain alkanes, and then the other two are named based on the rules that we established in the first presentation. So 4 carbons, the longest carbon chain, there's the butane parent name, and then you have a methyl group at the number 2 position, which is shown in that portion right there. In the second example, 1, 2, 3 is the longest carbon chain, and so you get propane as the parent name, and there you have the 2,2-dimethyl set of substituent groups for the first and second methyl groups, both at the number 2 position on the longest carbon chain. So just a little reminder of how we broke down the alkane nomenclature. And that method is used repeatedly with slight variations from one functional group to the next. But before I go on with the examples of nomenclature for this presentation, I want to get down the particular substituent groups that you need to know about. So you see methyl here, the CH3 group. I did ethyl last time. Let me do a little bit more formal analysis or breakdown of where these things are coming from. So those names for the substituent groups, they're coming from the modification of the structures and the structure and names for the series of straight chain alkanes that we saw here. And I'm going to look at the first four here: methane, ethane, propane, butane. And let me rewrite these here. Ethane, this is butane, this is propane. The analysis, if you will, that I'm going to show you here, this method to generate the different substituent groups, can be applied to any of those straight chain alkanes. But and you get sort of this, what feels like an infinite list of different substituent group names. But I'm going to stick with the handful that are shown on table 25.2 in your book. And so let me get all of them here in one place, so we know what we need to know for the test, right? That's always a good feeling. How do we get the different substituent groups? Well, it's easiest to show this process on methane. Here's the expanded structural formula for methane. It's just the simplest saturated hydrocarbon you can imagine. One carbon in the middle, 3 hydrogens. Well, what we've seen of this is, look back on that last slide. What does this sort of look like? It looks like what you've done is you've taken one of these hydrogens off, and now you have a different group. You have something that would generate some kind of branching point on the molecule, and then typically we draw it CH3. And then the squiggly line that I'm introducing here, this is just the rest of the molecule. For example, this squiggly line here would represent, the 4 carbon, longest carbon chain for this particular example. So just think of the squiggly line as the longest carbon chain here. And just sort of establish that trend every time we see a substituent group in this little slide here. And how do we modify the name? So we modified it chemically by saying we'll take a hydrogen off and then use that bond to just attach it to some larger molecule. And then we have a branching point on that molecule. And so we're modifying the structure. Let's modify the name. Well, what we do is we take that the A and E ending and just simply replace it with a YL. And that procedure is used for all of these substituent groups. So if I take off one of the hydrogens here, I would have a CH3CH2 group. What do I name that group? Well, I still use the IUPAC prefix for, base name for 2 carbons, F. I just change the ending to a YL, and I get my ethyl group. And I can do that for each one of these. Now, let me just show you here. So if I just take the straight chain and remove a hydrogen from the end, oops, should be a 2. I've removed one of these hydrogens here. I've attached it to some larger molecule, and then the name for that 4 carbon straight substituent group would then be butyl, and it's the type of modification you saw for the other 3 examples. Now there are 2 other possibilities for well, I guess I should say there's one more possibility for the propane. There's one more possibility for the butane that I want you to know about. And again, both of these they're both on table 25.2 in your textbook. And the one that the other one for the 3 carbon substituent group would be if I had taken a hydrogen off of the middle carbon. And what happens there is that then, where a hydrogen would have been, now I attach it to some larger molecule. And this particular substituent group is referred to as an isopropyl group. I do need to note one thing. You do use iso for the alphabetical order issue with the prefixes, and I'll show an example here in a few minutes. So ISO does matter for the alphabetical order for the IUPAC naming. Now the other substituent group for butane is actually coming from another an isomer of butane. So this one's a little bit more long-winded, so let me get the other isomer up here. So look what I have here. This is an isomer of butane. It has 1, 2, 3, 4 carbons, and it has the 10 hydrogens, just like we have here in this example. I've just connected the carbons differently. Now here what happens is that if I was to take this hydrogen and remove it, what I get is the other substituent group that's talked about in the book, and the other substituent group that we will use for our naming. And so now, again, what I've done is taken more highly branched alkane or isomer, constitutional isomer for butane, and I've removed this particular hydrogen, and now I would use that bond to then attach it to some large molecule, the LCC here. And this particular pattern that you see as a substituent group is referred to as a tert-butyl group. So the tert part here is tertiary. It's actually referring to well, I guess there's a couple ways you can think about this. It's ultimately the degree of branching at that first carbon is what it's talking about. And then the butyl part is just coming from the fact that you have 4 carbons. So the BUT is still consistent with the BUT in this other substituent group, or the BUT in this particular name for the alkane up here. And so these are the 1, 2, 3, 4, 5, 6 substituent groups that I want you to know and use for your different for the nomenclature for this chapter. And then for the alphabetical order for the tert-butyl group, you actually use the B here for the alphabetical order when you construct it in the name. You ignore the T in the front part. It's due to the fact that there's a hyphen between this descriptive term and the substituent group, versus there's no hyphen between the iso and the other part of the substituent group, if you will. I do not know the historical reason for that, and I just leave it at that. Take the B for alphabetical order here, take the I for the alphabetical order for isopropyl. Now let's actually use some of this knowledge in our next subject. So now I want to go through the process for naming cyclic alkanes, and it's another type of, I don't know if you'd call it a functional group. I guess technically I would describe it as the functional group as an alkane. It's just that now, because it's still a saturated hydrocarbon, you still have only carbon-carbon single bonds in your molecule, and you still only have carbon-hydrogen atoms in your molecule, but they're connected in a cyclic fashion. And so what we have up here is, I guess you would call this a condensed structural formula. And so the hydrogens that are shown on the side are attached to the carbons that they're adjacent to. But typically what you see are these geometric forms that are used, where the number of carbons and hydrogens are implied based on the structure. This is a very common way to draw molecules. There's even a convention to draw straight chain alkanes this way as well, called bond line form, which is what I typically use in my organic class. It's just an easier way to draw the molecule. If you're drawing a lot of these, you really appreciate these abbreviated forms, so you don't have to draw each carbon and hydrogen explicitly in your molecule. Notice the breakdown of the name. There's the only thing that is addition here is the cyclo prefix, and then the hexane, the pentane, the propane. They're still consistent with what you saw in this table here. You know, where you're essentially just taking the alkane name, and if that alkane is showing up in a cyclic structure, then you just throw cyclo on in the front. And then I would classify this entire region as the parent name. And so what we're going to see in terms of naming some additional cyclic alkanes, there's going to be branching points around the cyclic structure. Now, to tell you the truth, I think that naming alkanes are in some ways simpler than naming your straight chain naming your cyclic alkanes is a little bit easier. You still got to worry about your longest carbon chain, but your longest carbon chain for our purposes is always going to be the cyclic structure in your molecule. Let me just say this: that's not always the case, but that's organic chemistry, the 2-semester course where you worry about that. If you see a cyclic compound, this is the longest carbon chain, and we still have the issue about where do we start numbering the cyclic structure, because we still need to generate a set of numbers around this square here to establish where the chlorine is coming off or where the 2 methyl groups are coming off. So either one of these carbons that I've checked could be the number 1 carbon. Now we use that greatest branching rule to help us with that decision. There's 2 substituent groups here, there's only 1 here, so this is going to establish our number 1 position. And then if I number, in this particular way, either way around, the ring structure is going to put the number 3 position at the chloro group. And so that's not always the case. The next example would be an issue where one way is preferred over the other way. Okay, but right now we have everything in front of us that we need to build this name. So let me start with the prefix. Remember that's the substituent groups, and that's the chloro and the 2 methyl groups. Right? Methyl, they're both at number 1 position. Chloro is at the number 3 position. C comes before M, and so that is going to be first. There are 2 methyl groups here at both of the number 1 position. Oops. What did I do? There. 1,1 dimethyl is the name you'll want to use for that. Again, each substituent group has to have an individual number associated with it, and then we use our di, tri, and tetra to tell us if we have 2 or more of the same substituent group on the molecule. And then now the parent name here, remember the parent name, my use of that phrase, is dealing with both the base and the suffix. And for this one, it's cyclobutane. Cyclo, because it's a cyclic structure. Butane, well, there's 1, 2, 3, 4 carbons in a saturated ring here. In the next example, have a different ring structure. This is actually a 7-membered ring, and we have 2 branching points. So again, the LCC is going to be, the parent name is going to be cycloheptane. And then the question is, where do I begin numbering the two positions here? Because it's still, the branching point, we look for that, but there's a single branch here, a single branch here, so that doesn't help us. And so then we have to go to our alphabetical order list or rule for figuring out numbering the longest carbon chain, the cyclic structure. Up here is a bromo, and then what is this guy? Well, this substituent group has a total of 3 carbons, and there are 2 options for those 3 carbons. There's the propyl group here, and then you have the isopropyl group here. 3 carbons where the central carbon is attached to the longest carbon chain. That's what the isopropyl group is, and that's what we have here. We have the central carbon on the substituent group, and that's what's attached to the longest carbon chain. And so this is an isopropyl substituent group. B comes before I, and so the bromo is not only establishing alphabetical order for the prefix and the name, but in this particular example, it's establishing the order in which we number the carbon atoms as well. And so I want to begin, in this example, at the bromo position, because it's, again, both have a single branch point here and here, but this one has a higher alphabetical order. So I then number the ring so that I hit the other substituent group in the shortest distance. I don't want to go a long route to get over to the isopropyl group here. One comment I made in the first presentation is that when you number these things, typically what you see is that you try to reduce the actual numerical values as much as you can, and that's what you're doing here. By numbering at this position, you're putting the isopropyl group at the 3 position, which is lower than if I had taken it from the other side. And then just to fill it all out, there we see our 7 for the heptane. And now we need to construct the prefix for the name, and let me just move everything down here. I have the 1-bromo. I have at the 3 position, I have the isopropyl group. That completes the prefix, and then there's the parent name, cycloheptane. Okay, so that's the basic layout for naming the cyclic alkanes. And again, appreciate the fact that the rules for the cyclic alkane are very similar to the rules for the non-cyclic alkanes. In my opinion, this one's easier because you can see the longest carbon chain more easily than in the non-cyclic alkanes from the first presentation. Now, the other 2 functional groups that I want to focus in on here, they're both hydrocarbons. And they're both actually, I guess I could label this as unsaturated hydrocarbons. An unsaturated hydrocarbon means that, well, you have a double bond or a triple bond in your molecule somewhere. You have some kind of pi bond being thrown into your molecule. And like for unsaturated oils that in nutrition, you're dealing with olive oil or corn oil. These have very large molecules, and somewhere in that molecule there are some double bonds thrown in, 1, maybe 2 or more, and the term unsaturated fatty acid is used in biochemistry to describe that. And so all it's talking about is that you have an unsaturation point. You have a point at which that you don't have, it's not saturated. Saturated means that all of the positions around the carbons are filled with hydrogens, and here that's not the case. There's a double bond thrown in the mix. You've removed 2 hydrogens going from here to there. If you remove 2 more hydrogens here and replace it with a pi bond, then you would get your alkyne there. One thing I want to mention about nomenclature is the acetylene and the ethylene. These are common names. Honestly, I just want to focus on the IUPAC systematic approach for naming these guys. Before I actually go through the nomenclature procedure, let me just point one thing out to you. Let me remind you that all alkanes have this particular formula. All right? And so just like I described here, I removed 2 hydrogens here and I've thrown in a pi bond. Well, how does that change the ratio? And how it changes the ratio is, well, you drop the 2 there. And now what you see for the ratios of all alkenes, when there's a single alkene in the molecule, and those are the ones that we're going to deal with, is that the ratio is simply the number of hydrogens are doubled that of the carbons. And so for ethylene here, it's C2H4, and then for acetylene on the next one, the ratio that you see, I removed 2 more hydrogens to go from the alkene to the alkyne, and so what you see in the formula is that there's a -2, and you see that for acetylene. So anytime you have a single triple bond, it's going to follow this particular ratio. So again, these ratios that you see for the triple, double, and single bonds for the alkynes, alkenes, and alkanes can be used to tell you what you're dealing with in terms of if you're just given a molecular formula. And again, we're only going to deal where there's a single double bond or a single triple bond in the molecule in terms of naming the thing. Now, part of the name you can see in the group name, the functional group name. You have this ENE ending here, and that actually is what we're going to use for naming the alkenes in these examples, such as this one. Now, for alkene nomenclature, and what I'm about to say really goes for anything with a functional group, and the other one that we're going to concentrate on after this is an alcohol, but it's the functional group that you always focus in on to name the compound. Or I guess, yeah, to name the compound. And specifically in the beginning, you're using that to establish a number position on the longest carbon chain. And so, for example, in this one, I'm just going to go ahead and number the longest carbon chain. We see 5 carbons along the row, along the horizontal here. And I could have numbered from this position, I could have numbered from that position. Well, the rule states is that you number at the end closest to the functional group. The functional group is going to dictate not just the chemical and physical properties of the compound, but in this case it's going to dictate how you name the thing as well. And just in my humble opinion, just like that of the cyclic alkanes, it's a little simpler to name some of these functional groups because you establish the longest carbon chain based on the functional group, which is convenient. And then after that, everything else just falls into place as is. The only thing that you're going to see that's new is that the ending changes. But that's consistent with what we saw before. Like I said, the ending is going to tell you what your particular functional group is. So let me just put this name together so you can see everything. And there is one additional little aspect that I'm going to throw at you here. 3-methyl-1-pentene. And let's break it down just a little bit. This portion is just the prefix, just the substituent groups. And that's consistent with what we saw before. We have a 1-methyl group in the number 3 position, shows up in front. This part here, this parent name, it is analogous to the parent names for the alkanes. We have pent for 5 carbons, and then the ENE tells us that we have a double bond. We have a carbon-carbon double bond somewhere in our molecule. Where is that double bond? Because it could have shown up in any position along the longest carbon chain. Well, in this example, it's the number 1 position that begins the double bond. Now, let me do another example here using this guy. Let me draw it up here. I want to move the double bond just 1 position over, and it's going to change the name of the molecule. Going to change the layout of the condensed structural formula to this guy, and let me just check, make sure I got everything up here. I have 1, 2, 3, 4, 5, 6 carbons. If I look at my ratio, remember the ratio for all alkenes when there's just a single alkene in there is CnH2n. Well, in that example, the N is equal to 6, so the 2 times 6 is 12. And so that's where I'm getting this particular molecular formula for that compound. Well, do I have the same molecular formula up here? I do have the 1, 2, 3, 4, 5, 6 carbons. I see that. I have 3, 6, 9, 10, 11, 12. 12 hydrogens. And so it does have the same molecular formula. These two are isomers of each other. Okay? So that's one point that I want to make. I want to name this compound now. Let me switch back to let me use black on this one. Same rules as before. Again, I'm going to focus in on the functional group to establish the longest carbon chain. In this case, I'm going to need to number from this end. 5 carbons across the horizontal. I start at this end because it's closest to the functional group. Again, that's dictating how I number the thing. But notice the name. The name is very similar to the one before. The only difference is that 2 thrown in there. So now what is the name telling me? Well, I have a 5-carbon alkene, and at the number 3 position I have the methyl group, so I have the same branching as before. It's just that, where is the double bond kind of question? Well, it's at the number 2 position now, and you can see it there. Unique chemical physical properties, unique names. And that's what we see here. Now, the issue about isomerization for the alkenes get a little bit tricky for us here. And the way I've drawn this is not explicitly showing that issue that I want to deal with right now. That issue I want to deal with is it is a type of isomerism, but it's actually stereo isomerism. It's that other type of isomerism that I want you to be familiar with. And here's just a recap of a constitutional isomer. Has the same molecular formula, different connectivity. And on that last example, if we think about the different connectivity here, well, we can see a similar carbon backbone for these two. We have that branching point at the number 3, but there is a different connectivity. The double bond has been moved from one position to the next. So I'd argue these are two constitutional isomers. But there's an issue about this particular molecule. We won't deal with it directly. I'm going to illustrate that difference using a simpler molecule. And it's this issue of the spatial arrangement between two isomers. Okay, so what do we have here? We have the pentene series. It's a simple alkene with 5 carbons. We would say that's the number 1 position. 2, 3, 4, 5. And notice, we have to indicate the 1 in front here to tell me where is that double bond. If I block out that 1, pentene doesn't tell me anything. I mean, it tells me I got 5 carbons double bond, but it doesn't tell me where on this 5 carbon molecule that double bond actually is. You have to have the 1 or the 2 here to indicate where the double bond is. Well, what happens when you have the double bond at the number 2 position? Let me just lay this out for us. Number the longest carbon chain. Both the examples at the bottom, I am starting on the right-hand side with the number 1 carbon here and proceeding to find the longest carbon chain. There's no branching point here. There's a little bump in the road here, a little dip, but there's no branching point. There's no point at which an additional carbon branch is showing up. So there's no branching in these two molecules. But we do have a difference in the structure. What is that difference? Well, it's not molecular formula, but they actually, all 3 of these have the same molecular formula, C5H10. In the 2 bottom examples, they actually have the same connectivity. Notice, there's still 5 carbons that are connected in a row. In both cases, the double bond is still at the number 2 position, so you have the same connectivity. The only difference here is a different spatial arrangement. So the layout of the molecule around the double bond, the difference in layout around the double bond actually generates a different 3-dimensional structure for the molecule. For this example here, we have, actually, and I'm going to show a model in class about this, but whenever you have a double bond in your molecule, there's no free rotation here. Any single bond you have in the molecule, there is free rotation. And, we can't get into the nitty-gritty detail here. If you take the 2-semester organic class, you do see it. But there's all kinds of different conformational states that molecules can take on. They're not static little Lewis structures that you see on your piece of paper here or the screen here. These are very dynamic molecules. There's many different conformational shapes they can take on. There's different rotational and vibrational motions that they can take on. And in the context of the stereo isomerism, when you have a double bond in there, you have no free rotation. And I'll bring a model in to show that. But this position here, these atoms in this little block here, they're flat, they're planar, they're stuck. There's no way that this thing can rotate. If you look back at our little 3-dimensional shape for your alkene, again, it's a flat structure. There's that double bond, and there's no to rotate, to flip these. If I was to flag one hydrogen there, it's going to stay there. It doesn't have a free rotation there. There's no way it's going to be able to make it on that side. If it all of a sudden wound up on the other side, actually you would have to break the pi bond here to cause a rotation. And so these are much stiffer molecules, and as a result, there's a change in their chemical properties. That's one thing. But more importantly for us here is that, well, we need to name that differently. And the way we do it, there's a couple ways you can think about it. I would recommend, just looking for the hydrogens. How are the hydrogens laid out around the pi bond? If the hydrogens are on opposite sides of, one top and one bottom, we're going to use the label trans in front of the parent name, and actually in front of the entire name. Actually, if there's some substituent groups, we'll see that here in a minute. If there's some substituent groups here, trans would be out front. If the hydrogens are on the same side of the double bond, then we use our cis label. And so again, unique structure, you have a unique function, so we need a unique name as well. And we use the cis and trans to distinguish between the two spatial arrangements for the two pentene molecules there. Now, up to this point, I haven't said anything about alkyne nomenclature. Well, really, all the rules that I established here for the alkenes get used for determining the name of a compound with a triple bond as well. Let me just illustrate that with our acetylene molecule here. We have 1, 2 carbon atoms, longest carbon chain, the simplest alkyne that you can get, and the IUPAC name for this thing is ethine. And so we use the base names that we established in the first presentation, indicate the number of the longest carbon chain, and then the YNE is used to tell us where or what functional group that we have. Now, in the very last exercise, I do throw in an alkyne as an example, and so we'll see it there. But just remember that the rules for naming the alkynes are just the same as those for the alkenes. I guess the one thing to note is that there's no cis trans label. There's no stereoisomerism issues with the triple bond. This is a linear structure, and it doesn't give rise to any kind of difference in the spatial arrangement of the group. It's always linear, no matter how you substitute on either side here, which again is different here. This is, in one case it looks like a bend, in the other case it looks more like a zigzag for cis and trans for the alkene. Now, before we get to this practice exercise, which is the last slide, notice that there is one more character that we need to deal with. And just remember, from the first presentation, this is an aromatic compound. We see the structure here. Remember I said that we can use a donut or the circle in the middle, or we can use one of these two forms, this alternating double bond, single bond. Either one of these are valid. And we're going to use these notations to represent the aromatic compound, this flat structure, six-membered ring. Here's some examples here, and notice I'm going to stick with the ring in the middle to indicate that we have an aromatic compound. And so part of the job is just being able to recognize the aromatic compound is one thing I want you to do, and it doesn't matter if it's a monocyclic structure or a polycyclic structure. If you see 6 carbons with a ring in the middle, it's an aromatic compound. If you see substituent groups on the outside, it doesn't matter, it's an aromatic compound. And this one has a common name, toluene, which I won't ask you. I'll ask you to name something like this guy. And so we're going to use benzene as the parent name, and then we're going to name the substituent groups in front. Very similar to the other IUPAC methods that we've seen. Parent name comes on the right-hand side, substituent group names show up in front of the name. I'm not going to have you memorize naphthalene or anthracene. If I gave you these in the test, the only kind of question I would ask is, what is this an aromatic compound? It's that simple. Okay, so I'm not gonna. I just threw these up as some additional examples. The main thing you're going to see is something like this guy, where there's our toluene molecule again, and again, if I give it on the test, it'll be methylbenzene is the name that you'll need to be familiar with. This cyclic aromatic compound only has a single substituent group, so if I don't need to number anything, it's just there. It's just in the one position. It's the di-substituted examples where the prefixes get a little bit more complicated. And I'm going to use ortho, meta, and pair just because they're very common in organic chemistry. That's the one I'm going to stick with here. And then so notice the breakdown here. I'm going to, again, for all of the aromatic compounds we're going to use, benzene is the parent name that you're going to choose. And then, at that point, look at there's two issues. What substituent groups do I have? And how are they laid out around the molecule? So in all three of these examples, I've placed two nitro groups on the molecule, which is another substituent group I want you to know. So a nitro group is simply NO2. And I have two of them, so you see the dye showing up in all the names. But that the arrangement of the two groups are different. They have different connectivity, if you will. These are three different constitutional isomers for dinitrobenzene. And so if we have a unique compound, we need a unique name. If the two groups are side by side, we use an ortho label. If they have one carbon in between, then we use the meta label. If they are on either end of the benzene 6 system, then we use a para label. And I want you to use the ortho, meta, and para labels for the naming of any compound that has a dye substitution pattern on a benzene ring, such as the one that you see here. So what I would suggest that you do is to pause the video and practice on these 4 examples before turning it back on and seeing the answer. Okay, let's give these a shot. Actually, let me just do the aromatic compound first, since we were just talking about it. Notice the dye substitution pattern we have on opposite ends of the aromatic ring. So that's a para label. The para label here establishes how are the substitution groups laid out on the molecule. 2 bromo groups, so dibromo, and then the parent name is benzene. Let me do the other cyclic compound next. We have, this is a square, so there are 1, 2, 3, 4 carbons here. That's cyclobutane is the parent name for that guy. And then there's only one substituent group, so methyl. So you would give methyl cyclobutane as a name here. Notice that I don't necessarily have to put a 1 in front. If there's just a single substituent group on any kind of ring system, you don't need to show the name. Just like back here for the toluene example, the methylbenzene. If I put a 1 there, that's just a redundant statement. I mean, there's only one substituent group anyway. So, I mean, when in doubt, throw a number in. I'm not going to count it wrong or anything, but just know that it is a 1 there is not required to name this one properly. Whenever you give a name here, you need to be able to. I mean, when you view it, you need to be able to draw the thing. And so methyl cyclobutane is enough information to draw this particular structure. The 1 is not necessarily needed. Let me save this one for last because we got the cis-trans issue to work out there. Let me do this alkyne down here. Now, in both of these, you have a functional group now, and the functional group is establishing the longest carbon chain, and so that's good. In both of these, let me just go ahead and number, at least here through the functional group. Establishes at what position we start the numbering, and then here, let's see. Actually, it doesn't matter which way we go. This is the 3rd carbon, 4, 5, 6, 4, 5, 6. And again, like I said in the first presentation, it doesn't matter which of the longest carbon chains you number. In both cases, the longest carbon chain 6, no matter which way you go. It doesn't matter which way you go. It'll still give the same name. So I'm just going to stick with along the horizontal here for the 6 carbon, the longest carbon chain. And now we have a propyl group coming off of the number 3 position. That was one of the substituent groups that we went over in this lecture. It is on table 25.2 as well in your textbook. again, like I mentioned, alkynes and alkenes are named in a very similar fashion. We have the 1 here tells us it's the number 1 position that the triple bond is showing up. The hex tells us we have 6 carbons, and then the YNE tells us that it's a triple bond. That kind of breakdown can be applied to the alkenes as well. And so that's one reason why I didn't do a separate set of slides for the alkynes, because they're named essentially the same way as the alkenes. Again, the only thing different here is that you don't have the stereoisomerism issue. There's no cis-trans, there's no label that we have to put in front here. That's not needed because this is a linear structure anyway. There is no, depending on how you change the groups around this triple bond, it doesn't change the three-dimensional shape. It's always linear. Here, I guess, technically each one is a trigonal planar geometry and it's a flat structure, but it matters. In this particular one, you have 2 hydrogens on the same side of the double bond, so you're actually going to see a cis label for this particular example. But if I was to switch this methyl group to this hydrogen, then I would generate the other stereoisomer, the trans structure. And so with the double bond, just make sure you look for that, the cis-trans label. And then let's see, after that, we still need the longest carbon chain, 5, 6, 7. So this is actually a heptene. 2 heptene actually would be the parent name. We need a 2 there to tell us where in the world is that double bond. And then we have a methyl group at the number 4 position. And so this is one of the examples where I mentioned earlier, cis and trans show up at the very front of the entire name. So it even shows up in front of the to the left of the substituent groups. And then finally 2 heptene for the naming of this guy. And that's it. That covers the full treatment for these different functional groups. In the next presentation, I want to do 2 main things. Introduce you to a few more functional groups that you need to be able to recognize, and then we'll go into a little bit more nomenclature, but not too much more. We're about over. We're about finished with this. Okay, thanks.